Now I know where there's lots of these pens because they're all destroyed. Okay.
Oh.
Only this one. Yeah, for some reason the low order ones, the tip falls into the pen easier than on the other one. So
low odor?
This one is.
Because this is the ones I used to from the math office. I found when they're new, they're still pretty smelly.
Oh no, those are not low odor. Those are bold color. Bold color are not low odor.
Oh,
okay.
I see.
If you always smell and use the bold.
That's why they're so smelly.
Okay. Okay. So are there any questions about the homework now? Now that we've had some time for it. Anything left? Okay. I do want to comment something about Bessel's inequality. Last time we did spend all this time on Bessel's inequality and proved it so that X be an inner product space Bessel's inequality one more time. And let E1, E2, and so on be an orthonormal sequence in X. Then we showed that last time we showed that the norm of x squared is greater than or equal to the sum k goes from 1 to infinity of the square of the absolute values of the Fourier coefficients. And we kind of went a little bit of a long-winded proof. It's not that difficult actually to prove this, because you can see quick proof. You simply write y1 equals summation k goes from 1 to n x ek, and then you show that x minus y1 is perpendicular to E1 through En. That's quite easy because you just use the inner product and it falls out. Okay. Perpendicular to this, not equals. Okay. Okay. You just by inner product by direct calculation. With inner product. And so what would happen after that? Therefore, since y1 is in this space, you've got something perpendicular. This is perpendicular to the subspace generated by those n vectors. So you get a Pythagorean relationship immediately. So you get that x minus so you get norm x squared equals norm x minus y1 squared plus norm y1 squared. Okay. And so you get, therefore, norm x squared is greater than or equal to the norm y1 squared. But the norm of y1 squared is equal to the summation k goes from 1 to n of the absolute value x ek squared. Okay, and therefore this is a bound independent of n, and therefore you can let n go to infinity. So this is a quick and dirty proof of Bessel's inequality. What is actually done in the text is something more. You actually show that this y1 is the solution to the best approximation problem. We also showed, however, the proof last time showed that y1 is the solution to the best approximation problem. So that doesn't fall out from this quick little proof. Okay. You have to do a little bit. You have to use the projection theorem. That's what we did last time. That's why I'm saying that I want to review this just a little bit. Therefore, x squared is greater than or equal to the sum k goes from 1 to infinity. X ek squared. Okay, so that was Bessel's inequality. The quick proof. The Bell's approximation problem. X minus y1 equals the delta equals the minimum of the distance between x and y tilde belonging to the span of E1 through En. Okay. So we actually said that if I wanted to approximate x by a vector, in the span of the first n of these orthonormal vectors, okay, by the span of those first n, then I would choose this finite Fourier series to do the job. So I'm not going to go back to the proof of that by the projection theorem, followed by projection theorem. 3.3-4. Okay. All right, so no, we all know the answer. It's a little painful sometimes to go through it, but that was the thing. So now, what is the classical application? Classical application is in Fourier series. So let's just take a little detour into Fourier series. It's just going to be kind of to show the lay of the land and give you a little bit more something to chew with. Okay. All right? Because we're not going to actually go and prove everything about Fourier series. We're not going to do a course in Fourier series, but let's have an example. So, and because he wants to motivate this coefficient being called the Fourier coefficient. So by way of motivation, there's a section on Fourier series. And so let x of t be a 2 pi periodic function, real valued continuous function. I'm going to take real valued continuous function. So 2 pi periodic means it's going to be a function on the line, on R. Okay? And we can hope to represent x of t by a trigonometric series of the form a0 plus k goes from 1 to infinity. There are two terms in here, there's, as you've all seen in previous applied courses, I'm sure, differential equations, what have you, if you ever had a course. AK cosine kt plus bk sine kt. Some infinite series expansion like this. The cosines and sines all have period 2 pi. And so the only question is whether we have enough functions here, okay, to represent the continuous function. So, where is this coming from? Well, it's known that you can do it in some cases. All right, but the general continuous case cannot be handled, it turns out, because the continuous is just a little bit too much. If you want, that is, you want pointwise convergence. Represent. So what do I want? It turns out that it can be done if I want to represent it as an L2 limit. Okay? But if I want to represent it as a pointwise limit, that's a different story. Remember, we have different... if I have an infinite series, then I'm talking about convergence of the infinite series. But in what norm? Or in what sense? Okay? There's different senses. Okay? So I can talk about convergence in the L2 norm. I can talk about convergence in the C01 norm, for example. The uniform norm. Does that exist? And then something sort of in between, does it just converge pointwise? There's not a norm associated with that. Okay, so those are some of the things we want to look at in the general picture. Okay, let's show, though, that this series arises naturally. Let's show how the series arises naturally for the Hilbert space. For the Hilbert space, L2, 0, 2 pi. Okay. Now, I'll recall what this Hilbert space is. There's two ways we could look at this Hilbert space. One was the completion of C01. This is the real one. We're just going to talk about the real L2, 0, 2 pi. Okay? One way was this is the completion of the real C01, C0, 2 pi with inner product xy equals the integral 0 to 2 pi x of t, y of t dt. Okay, this is an inner product on C0, 2 pi, but it was not but we did not have a Hilbert space. In other words, you had an inner product space, but not a complete inner product space. Okay. And there was a general formula for that in the book that's described in the text, which we didn't go through the proof of the general completion process. We should do that someday, maybe, just for the heck of it. It might be fun. And then there's another idea that actually Lebesgue had constructed another way of looking at L2, 0, 2 pi, and that is it's square integrable, Lebesgue square integrable functions. Lebesgue square integrable functions, also as, which is a little bit maybe easier to understand right now since we didn't go through the completion theory.
That's how they came about, because of Fourier series.
Yeah. Yeah. I believe so, but I don't know the whole story. You're going to have to tell us in your thesis, right?
Dr. Colt told me that's why, because it wasn't enough.
Right.
Riemann integral, but I don't know the whole story.
Yeah. Yeah. No, definitely Fourier series. We're in on the game. Yeah. You can guess because of this connection right here.
Right.
So presumably Lebesgue said, "Okay, I'll figure out what this completion is," and so then he constructed the Lebesgue integral. Okay, to do it. Okay. But you can tell us the full story.
I'll have to ask him.
You might have to study about it.
Yeah.
Okay. Anyway, asking is a good start. So there you have it. And so where Lebesgue square integrable function is actually what you have there is the space. One function, the points in that space are not single different functions. In other words, two functions are equal if they're almost everywhere equal. Or almost everywhere could be as big as a countable set or bigger. In other words, they could differ on a countable set or more.
Everywhere the measure is not 0.
Yeah, in other words, the set of points in which the functions differ just simply has to be of measure 0.
Right.
For example, the Cantor set. They consider to be differing on an uncountable set. The Cantor set is uncountable with measure 0. So as long as the functions differ on the Cantor set, hey, they're the same function according to, this definition. All right, so it's the equivalence class of functions that are almost everywhere equal. However, if two continuous functions are almost everywhere equal, they're actually equal. Two continuous functions are almost everywhere, because if they're different at a point, okay,
right,
then they'll be different in a whole neighborhood of the point, okay? And so then, if you take the difference of the functions and square that and integrate, just that interval will contribute enough to blow the L2 norm greater than 0. And therefore they won't be equal in L2. So two continuous functions would have to be equal everywhere. if they're equal in L2. All right. Okay, so two continuous functions that are Lebesgue almost everywhere equal in L2. Well, they're almost everywhere equal that are equal. Well, let's put it this way: almost everywhere okay, that are equal in L2, 0, 2 pi, must in fact be equal pointwise and not only almost everywhere equal. In the Lebesgue sense. Okay. So the integral is set up so that if two functions are almost everywhere equal, then their square integral is going to be the same. It's not going, the set of measures 0 is not going to affect the integration. It just won't. It's just like multiplying something by 0. You get 0. Okay. 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 So, where are we going to start? Let's take a specific example. First, I want to get an orthonormal sequence. Orthonormal sequence. Trigonometric sequence in L2, 0, 2 pi, is as follows. I claim that claim is that 1 over the square root of 2 pi, 1 over the square root of pi cosine t, 1 over the square root of pi sine t, comma 1 over the square root of pi cosine 2t, 1 over the square root of pi sine 2t, etc., is an orthonormal set, is an orthonormal sequence. In L2. Okay. And how do you verify that? Have you all seen this before? Okay. So I have a constant function that I've normalized. I've got a cosine that I've normalized. A sine. So you said no? You haven't seen it before?
I've seen it.
You've seen it before? Is there anyone who's never seen it before? Well, maybe we should just go quickly. Then you have, how do you know that the constant is orthogonal to all these other ones? 1 is perpendicular to sine kt and cosine kt for all k. How does that work out? You just have to integrate 0 to 2 pi sine kt or cosine kt. I'm going to do 2 at once dt. Okay, like this. And you get, let's see, you simply get, and k is not equal to 0, all k greater than or equal to 1. Okay? Then you have minus 1 over k cosine kt, 0 to 2 pi, and you also have 1 over k sine kt, 0 to 2 pi, and those are 0. Okay. So the constants are orthogonal to those. Then you have to show something else. You also have now. What about the normalizing factor? Well, the 1 over the square root of 2 pi is obvious because I have to take the square root of the square integral of 1. Right? So I'll just skip that. What about the square root of pi? I didn't know that. If I do normalizing factor, so I'm going to do that next. 1 by the square root of pi, what you do is you take the integral 0 to 2 pi of cosine squared kt or sine squared kt dt. Actually, you can argue that those integrals are the same by shifting, by just the graphs of the curves that we're familiar with. They're each equal, and their sum gives you 1. So each of these integrals is equal to pi. Maybe that's the way I'm going to say it. Okay? Use the good old trick. Equals 2 pi divided by 2 equals pi. Okay? Show that they're equal because you're on the full period. And then their sum is equal to 1. Use that. Sine squared kt equals integral 0 to 2 pi cosine squared kt dt. Okay. Then I have to do some work, though. Then I have to consider the inner product of any cosine with any other cosine, and any sine with any cosine, and any sine with any other sine. So how do I do those? And any cosine with any sine. I didn't even do the any cosine with any sine on here, but that's almost the same method. So how do I do integral 0 to 2 pi cosine, I'm just going to do m and n, cosine mt cosine nt, or sine mt sine nt. How do I do those? dt. Well, I use the angle addition and subtraction formulas. This is 1/2 integral 0 to 2 pi cosine m minus nt. Let's see. That's with the cosines. It's a plus, I believe. Plus or minus. What I've got it here, cosine of m plus n t, and then dt. Let's check this. Let's see. If I took m equals to n with the cosine, then I get the double angle formula for the cosine. So that's cosine. That's 1 minus cosine 2 minus twice the angle. Let's see. Is that right? 1/2 is 1/2. 1 minus. It doesn't look right. Yeah, that's right. 1/2. 1 minus cosine of the double angle equal to the cosine squared theta. That corresponds to cosine of the double angle equals 2 cosine squared theta. Let's see if I got the sign right. Okay, this, but the other minus 1, which is correct, I believe. Okay? Well, you can check this at theta equal to 0. Everybody knows that one. That's wrong. Oh, I said plus. That is correct with a plus sign. At theta equal to 0, it's correct. Okay. All right. So anyway, that's the correct formula. Using the angle addition and subtraction formulas. And we just showed each of these integrals as 0. By the same method over here, because you have the integer, the full integer of frequency. Okay, equals 0, and then similarly, integral 0 to 2 pi, a sine mt cosine. This is for m unequal. This is for any m and n, and then sine mt cosine nt for any m. This is for m unequal to n. That's right. This is for m unequal to n. And for any m and n, this one, equals to 0. You have to use the angle addition and subtraction formulas for the sine. So I guess for even if m equals n in that case, the reason is if m equals n, you get trouble if you put the cosine. But if you put the sine, you get 0, right? Okay. So for similar type calculations. So anyway, we've kind of checked it anyway. Okay? Everybody with us? We have the orthogonality of these functions, this system of functions. And then we've also got the correct normalizations. Okay. So let's do one, just for practice. You've all seen it before. But for completeness, I'm going to stick it in here. So what if I... let's just point out, the author suggests this possibility. If the series, just perhaps, A0 plus summation AK cosine KT plus BK sine KT, K goes from 1 to infinity, were to converge uniformly, all right, and then it would be, of course, converging to a continuous function. Pointwise converging to, and uniformly converging to a continuous function, because the partial series are continuous functions. So if I had uniform limit of continuous functions, I get a continuous function that's... didn't we do that already? Uniform, yeah, we had completeness of C01. Okay. Uniform limit of continuous functions is continuous. That's the completeness of the continuous functions. Okay. Continuous function by completeness of C0 to pi. Okay. Then what could we do? Then you could integrate term by term by uniform convergence. That's a theorem from the Math 532. Okay, for the good old Riemann integral. Okay. Then we could recover the coefficients by term-wise integration. And have the following series: x equals x E0 plus summation k goes from 1 to infinity, x ek plus x ek tilde. So let's just show an example of this, where ek tilde is going to be, this is going to be E2 tilde. He's going to, because he's got the sines and the cosines, he's calling this E2 tilde. He's calling the cosine E2. And he's calling this E0. 1 over the square root of 2 pi, the E0. These are the orthonormal ones. E1 is this one, E1 tilde is this one. Okay. Yeah, he just has to have a notation. Because you could take the evens and the odds. You could also do it that way. But instead, he doesn't want to have to count even and odd, so he's just going to call the signs the tildes. And so he's going to have instead of having an orthonormal sequence, he's going to have 2 sequences. Okay? And paste them together. Okay. So, actually, you could figure out what the formula for the... Okay, so So if this was x of t, if you just had, if I just had this series, so I'm not saying I started with the function x of t. Let's put it y of t. Well, I call it x already. Okay, I call it x. Suppose I've got this thing where to converge uniformly. Okay, to a continuous function. So x of t would then be a continuous function. Okay, then we could recover the coefficients by termwise integration and have this. What actually are the formulas then? You would have that you would inner product. Well, you would have that AK cosine KT would have to equal to the inner product of x with the 1 over the square root of pi cosine KT times the 1 over the square root of pi cosine KT. So you would have to have that AK equals 1 over pi integral x of t cosine kt dt 0 to 2 pi. Okay, so that's the formula for AK. And similarly for the other ones, BK with the same thing, 1 over pi, and then the A0, that's with a 1 over 2 pi. Okay. All right. So if we do this, let's say, so now the question is, if we start with a continuous function and develop it this way by generating these coefficients, okay, does that actually give you back the original function? That's the question that usually burns in people's minds when they look at this subject. Okay, or they just say, of course it does. It remains to ask if from an applied point of view it doesn't make any difference, you're only going to do the finite dimensional approximation, whether a given continuous function x of t on 0 to 2 pi periodic, it's a given continuous function 2 pi periodic, x of t has a representation, well, I'm going to call it star or something like that. Star. Okay. That converges pointwise. In other words, is it true for every single fixed t that this infinite series converges to the number x of t, if where x of t is given? So, in other words, I start with an x of t, I generate this series, does it actually equal x of t for each t? What we're going to be able to show by Hilbert space theory is that if I start with an x of t in L2, okay, and I generate this series by writing out this Fourier series, then I will get, as long as the orthonormal sequence is total, okay, which means that there is no function in L2 which is orthogonal to each one of these given ones. That's what it's going to be one of our criteria. Then you'll have convergence in L2. Okay, you get convergence in L2. But that doesn't mean pointwise convergence necessarily. So, this turns, okay, so the question is converges pointwise. This turns out not to be true in general. Okay? However, if x of t is of bounded variation, and periodic, then one can show that the Fourier series converges to the following function: 1/2 limit h goes to 0 from the right, x of t plus h. This is plus x of t minus h. You'll have these left and right limits, okay, for a function of bounded variation, and this will be the actual function you'll get. So you've seen that before. If you take something like, I think you've seen it before. You take something like a step function. It's say pi over 2 and then pi. This is going to be a periodic function on minus pi to pi, something like this. Then you're going to get so here's the midpoint. Okay, here's the average of the limits from the right and the left. 0 if these are at height 1, let's say, and minus 1. This is the function. So this is my x of t. The Fourier series will converge to this mean value. Okay, this is a function. What is a function of bounded variation? That's a little bit. Most people don't have that definition at the tip of their tongues. Okay, or their minds. You basically have to take. What you take is any partition. You take the soup over all partitions. X 0, x1, and so on, x n of 0 to 2 pi. I can say 0 to 2 pi, or it's 2 pi periodic, so it won't matter. And then I take x of t k, or I minus x of ti minus 1. Take absolute value and take the sum like that, and this should be finite. Okay. Bounded variation. So, for example, if it's piecewise monotonic, that will do the job. Okay? And be a bounded variation. I believe that's the correct. It's not in this book. You'll have to look some other book on Fourier series. But you can be the expert. You can tell us all the answers. Anyway, so it's on this bounded variation. This is from that Kenneth Hoffman book that I pulled this thing. It's one of the problems at the end of the first or second chapter. Okay. Okay.
Actually, maybe the finite case of that on page 225.
225? Okay, let's have a look at that. Maybe it does have something in here. 225. Okay. Where? Application of bounded linear functionals. Oh, okay, there he has the variational norm. Okay. Total variation. So to be a bounded variation with this. We just have the definition of bounded variation. I don't know if he's got the... what you can basically do with a function of bounded variation is you can do integration by parts still. That's the basic thing about it. Okay. So it doesn't have to be continuous or differentiable or anything like that, but you can still do an integration by parts formula. So that's pretty useful. And that comes in. I don't think he's going to do the Fourier series associated with it, though. Looks like. Okay. Okay. So the definition is in there. Very good. All right. So you have this. So this is, I think, the classical thing. You've seen this before. You get this Gibb phenomenon, and then it goes like this, and then it goes like this. Oops. Okay. The finite series. Okay. All right. So you can't hope to get it even if it's a continuous function. Okay? Because continuous functions are going to be pretty weird. Okay? They don't have to be bounded variation, for example. Some of these fractal examples, like a function which is continuous but nowhere differentiable, and they have all these, little tiny bumps everywhere. You can make the variation norm for infinite on those. Okay? Okay. It's not proving that you don't get convergence of the Fourier series, but that's at least not showing that you don't have that. So a good counterexample for the continuous one, I don't think I've ever seen that. So I'm sort of saying this a little bit blind because it turns out to be not true in general, but I don't think I've seen the counterexample. At least not that I remember. Okay. Okay. So what do you have, though? It follows by Bessel's inequality that we're going to get convergence of the trig series just by Bessel's inequality in L2. So by Bessel's inequality, the series, what we have is we obtain that 2 pi a0 squared plus pi summation k goes from 1 to infinity ak squared plus bk squared is less than or equal to the square norm of x. Okay. So that the infinite series a0 plus summation ak cosine kt plus bk sine kt 1 to infinity converges in L2 to something. L2 to something, okay? Not necessarily x. And to know that it actually converges in L2 to x, I'll need the totality, okay? And I'll obtain that from the totality. That's going to be followed by the totality. To something, okay? The convergence, okay, how do you prove this? Proof of this statement. Proof of this last statement is given in 3.5-2, which we stated last time but didn't prove. Okay, so it's only going to use Bessel's inequality. How do I prove that this can, so here's the statement of the theorem. Let H be, so let's go ahead and do the abstract thing. Okay, let H be a Hilbert space, and let EK be an orthonormal sequence. Then A, the series, I'll call it double star, okay, because I already used my star, summation alpha k ek, so I'm just going to do it more abstractly, but you can see the immediate application to the trig series, converges in H if and only if the sum of the squares of the coefficients converges. Okay. Further, in this case, B, in case this A, okay, we can write, we actually know what the coefficients are, we can write that the alpha k's is equal to x ek, where x is the limit x equals the limit sum k goes from 1 to n alpha k dk. So I have to call the limit something. Unfortunately, x gets used, you're thinking about x as the original function, then you're also thinking of x as the limit, so you have to keep your x's straight, right? I could call it y. I could say this is y, where y is the limit. This might be easier to understand. Okay, where y is this limit. I'll call this y, right? Because y need not be my original vector x. I'm just constructing a Fourier series. Okay, then the Fourier coefficients are the Fourier coefficients of this limit. Okay. So, for example, if you didn't have all of the trig functions, you just threw away the sines or threw away the cosines. Okay, you would still have a series. Okay. And as long as the sum of the squares of the coefficients was finite, you would still, in other words, just throw away some of the things. Okay, I'm going to ignore half the terms. Okay, then I certainly have convergence to something. Okay, that's my y. All right. Well, that's what the statement of this theorem is, that I will have convergence to something and call it y, and then the coefficient is the Fourier coefficient of y. This discussion makes sense here because we're still not maybe convinced completely that the trigonometric system is total. Maybe you can't cover all the functions in L2 this way. Okay, so that's all this theorem is stating, though, that you're getting convergence to something. Okay, and then there's a part C of this theorem. Finally, C, I guess this is a discussion. Finally, C, if y is in H, then the series double star defined by alpha k equals the inner product of y with ek converges in H to, I should put this if x is in H. If x is in H, then the series converges to an element y. I should put x here. I'm going to go back to given the x in the Hilbert space. Converges to an element y in H, though y need not equal x. Okay, when ek is not total. And we'll see what total means below. So we'll see what total means below. This is C, statement C. I might have changed the notation a little bit from the notes. Sorry about that. But you have to deal with the x versus the y. What I'm thinking is x is my given function in H, and y is the limit of this trig series that might not quite equal x. Okay, might be close, but not equal. In other words, there might be strict inequality in the Bessel's inequality. Okay, is what it's going to boil down to.
Right. I think it makes more sense that way.
Okay. Now, okay, so we could do an example. I think I put one in the notes, but maybe we should prove this theorem first. Proof. How do you prove this thing? A, how do you know that this converges if and only if the series is finite? This is going to follow pretty easily because what I'm going to do is I'm going to put Sn equal to the sum. This is A. Sn equals the sum k goes from 1 to n of alpha k ek alpha k times ek. Okay, and now I'm just going to go ahead and show that this is a Cauchy sequence. If and only if the sum of the squares of the alphas converges. You simply compute Sn by orthonormality. Sn minus Sm norm squared is the sum. K goes from m plus 1 to n of the alpha k squared. Okay, which the author calls sigma n minus sigma m, for sigma n equal to the sum of the squares of the alpha k's. K goes from 1 to n. I can always define that no matter what the alpha k's are doing. Okay, I can always define the finite sum. So I define these finite sums. So I have the square of the norm of the difference is equal to simply sigma n minus sigma m. And now, do the if and only if. Therefore, if Sn converges in H by completeness, Sn is Cauchy. So that means that this is less than epsilon for all n and m sufficiently large. Therefore, the sigma n minus sigma m is less than epsilon for all n and m sufficiently large. So, sigma n is Cauchy in R. Because one is Cauchy in H, so the other one is Cauchy in R. All right? And therefore, the sigma n, since R is complete, the sequence sigma n converges. That's all that's being used here. I have two sequences, Sn and sigma n. One in H, one in R. This is Cauchy in H if and only if that one's Cauchy in R. If this is convergent in H, therefore, it's Cauchy, and therefore this is Cauchy, and therefore convergent. And vice versa. Okay? So that gives A. Simply by going to the Cauchy condition. Conversely, so sigma is Cauchy in R, so convergent in R. And that's exactly what I want. I just want convergent in R. Because if sigma n is convergent in R, then, of course, the infinite series is finite. That's what I mean by convergent. It means the infinite series converges. Conversely, if sigma n converges, then it is Cauchy. So, Sn is Cauchy. So in H. So convergent in H. Because we've got the Hilbert space here. We've got the complete norm space. Okay, so that's A. B simply follows by the good old continuity of the inner product. We can write alpha k equals y e k. In other words, write y equals the limit Sn for B. Write y equals the limit Sn in H. Okay, that means in the norm of H, the limit is holding. So, y e k, is that what I wanted? Equals limit Sn e k, n goes to infinity, equals alpha k e k by orthonormality equals alpha k. In other words, when n is sufficiently large, then the kth term is going to appear in the sum, And when I take the inner product with ek, then all the other, this is a finite sum, okay? This is a finite sum, so this is summation j goes from 1 to n, alpha j, ej, and then inner product with ek. When I actually do that, assuming that n is big enough that it's past k, which I can always do because I'm fixing k and letting n go to infinity. So I fix n big enough that it's past k, then compute this. This simply comes out to be alpha k. All right? By orthonormality. So, you're done. K equals limit alpha k. Limit alpha k, limit of a constant. Limit of a constant is the constant. Limit n goes to infinity. Okay. So it's the limit of the constant. As long as n is bigger than k, then I have the constant sequence. Before that, it's just 0. Okay? So 0, this limit sequence is 0, 0, 0, 0, 0, 0, then alpha k, alpha k, alpha k, alpha k, all the rest of the way. As soon as n is bigger than k, it becomes alpha k, alpha k, alpha k. You kind of following what I'm doing there? You use this, I think you use this on like 10 different problems in this chapter. This trick. Or 10 different problems plus proofs, I guess, combined. Anyway, it gets used all the time. This continuity of the inner product. Okay. So part C is that if x is this converges in H. Well, that's by Bessel's inequality. C by Bessel's inequality. And that's what we actually used in the application. Because what we said was we used by Bessel inequality and A in part A. Because what we said was you've got x squared is greater than or equal to summation x ek squared. Okay. So, and that's, okay, therefore, this is a finite number. Okay? If x is in H, then that's a finite number. Because the norm is finite, okay? So by A, with alpha k, by part A, with alpha k equal to x ek, we have the summation alpha k squared is finite, so then, summation alpha k ek, k goes from 1 to infinity, converges to some y in H. Okay. Converges in what we're thinking about in terms of L2. It converges in L2. So I do get convergence. Okay. I think I'll have to skip the trig series example. You can read up where I get the sum of the reciprocals of the fourth powers of the odd integers. Okay. Okay, get a formula for that. Classical one. One thing I was going to add to the end of that line was you're going to get convergence. So let me just add the following lines right before I discuss totality, which I didn't get to today. Well, let me just give the definition so that I can say what totality is. Totality an orthonormal set. And now he's going to talk about sets in general, because he wants to consider that he can consider the uncountable case almost as easily as he can consider the countable case. There's only a little bit of messing around you have to do. He does a pretty good job with that. I don't want to spend a whole lot of time on it, but I'm just going to go ahead and make the definition here anyway. So I've got a possibly uncountable index set I and kappa instead of k. When he does that, that's a kappa. Lowercase kappa is what that's going to be there. Okay. is total in an inner product space even. X if M equals the linear span of this orthonormal set, which means you take all possible finite linear combinations, and that's a vector space, right? Take all possible finite linear combinations, and now close it up. If M gives M bar equals X. In other words, if the closure of the linear span of these elements is the whole space. Okay. And then we're going to have a theorem about that. Now, it turns out that the trig system and the reasoning behind that is simply going to be the same reasoning they give at the beginning of section 3.7.1 for the totality of the Legendre polynomials. It's going to have to do with density. The trig system is total in L0 to pi. So, for example, the Fourier series, which I didn't have time to develop here, in the notes for x of t equal the periodic extension of the function of, let's see, what did I take? I took absolute value of t on minus pi pi. So I took a function that looked like this. I'm really out of time now. Shoot. This was pi, and this was minus pi. Okay, I just took the absolute value of t, and I took this one. In the notes, I did this one, and I developed it as a Fourier series. I found the Fourier series is pi over 2. This goes as pi over 2 minus 4 over pi. It was a cosine series because it's an even function, over 1 plus cosine 3t over 9 plus cosine 5t over 25. So you're getting the reciprocals of the squares. Of the odd integers, okay, plus dot dot dot. Okay, this thing converges in L2 to the x of t. All right, the x of t, and that's all I said in the notes, other than computing what the L2 norm of this is. So by totality, okay, will turn out. Okay, there's nothing more that I can get. I didn't prove this yet. Okay, proof next time. Proof that totality implies convergence in L2 to original function in L2, original x in L2 will be by Parseval relation. Proof of Parseval relation. So I left that out. Proof of Parseval relation. So you're going to have to use it this weekend for your homework. Are you feeling that you could do that?
I've seen it before, but
okay.
I don't know if other people have.
So it converges to xt and L2. Now, it turns out, though, this is also uniformly convergent because the reciprocal, let's see, these are the k squared in the bottom, right? So also uniformly convergent. Therefore, what you would have is that you've got the partial sums would be converging uniformly to something, okay, which is in L2 because the continuous function is in L2. And the partial sums would also be converging in L2 to something, okay? But if I have uniform convergence, then it automatically implies L2 convergence. So I would have the partial sums converging, right? Uniform convergence would imply L2 convergence. If you have uniform convergence, you have the difference is less than epsilon. So then the difference of the square would be less than epsilon squared. Take the integral that's less than epsilon squared, then take a square root less than epsilon. So uniform norm automatically implies L2 norm less than epsilon. Okay. So if I had uniform convergence to y and I had uniform convergence and I had L2 convergence to x, okay, well that means I have convergence to two different things. Well, that's impossible, right? There's only one uniqueness limit. Therefore, y has to equal x in L2. But now if y equals x in L2 and y and x are both continuous, then y equals x. So for a particular example, you can show, using the totality, that indeed this does converge. Okay, to the original function pointwise. So you have xn or Sn minus y L2, well, uniform infinity goes to 0. You have Sn minus x L2 goes to 0. This implies that Sn minus y L2 goes to 0. Okay, so you have y equals limit Sn equals x in L2. You have in L2 two different things potentially which have the same L2 limit. Okay, so that means y equals x in L2. This was a both y and x are continuous functions, therefore y equals x. Therefore y equals x. Okay? So in this case you would get that the series converges by what we'll be able to prove. So even though we're not going to do a full thing on Fourier series, at least you can know that your certain classical examples are really good. Okay. So look here, uniform convergence of the series of Fourier coefficients. Absolute convergence. Excuse me. I needed absolute convergence of the coefficients, which is a very special case. Absolute convergence of the coefficients is not that common. Okay. When you just take, if you're just taking any old continuous function, that's not going to be the case. Lots of these Fourier series are conditionally convergent. Yeah. Okay. Well, we want to way over. Are there any questions? Last questions? Okay. We still have 2 minutes. Sorry, I thought class got a 1:20. So maybe I kind of hurried through this because I thought we were out of time. So all of this hinges on the totality. This argument here. All of this hinges on the totality. So totality implies this. Okay. This was simply by uniform convergence, okay, where y is a continuous function. Okay, so let me just finish this little argument that I had here, and then we'll leave right on time. This was 5t. Okay, so if I have this series, I can call the partial sums Sn as I did before. Because I have the coefficients are actually absolutely summable. You had summation 1 over 2k plus 1 squared. That's finite, right? All right. And since the cosine is bounded by 1, this is a uniformly convergent series. All right. Sn uniformly convergent. to a continuous function. But we only said, well, maybe y is not equal to x. Okay, but we know that Sn converges to x, the original function, by totality. In L2 it converges. Okay, but if I have uniform norm, then that automatically, so if I have integral s, if I have Sn minus y, and I take that squared, and I integrate that 0 to 2 pi, since this is less than epsilon uniformly, this will be less than epsilon squared times 2 pi. Okay, for n greater than or equal to capital N. All right, sub epsilon. So, by uniform convergence. So that means that Sn minus y, that's because I'm on a finite interval here, I'm using that. Okay? Therefore, Sn minus y, L2, goes to 0. Okay. So what I had was therefore limit Sn equals x equals y in L2. So I've got the same function in L2. Two continuous functions in L2, we mentioned already they had to be equal. Okay. All right. So we'll do the totality theory next time and finish this thing up. I think you'll be able to do. I did change assignment 3.7 number 3 to an extra credit problem, because it turns out there's pretty fancy manipulation with infinite series. Pretty nasty looking, so I made that an extra credit problem if you get through it. They tell you what the answer should be in the book, so it is doable. But you got to play like crazy with your series. Both 3 and 6 are extra credit, yeah. I'm only making you do problem 1 from 3.7.
Yeah, right.
So 3.7 is not the real difficulty. You'll have to read this totality theorem on your own, I guess. Okay. Thank you.